with this kind of system by just taking advantage of the technology which was successfully utilized to increase the capacity and reliability of optical fiber networks, which include WDM and fiber amplifiers. And I would like to note that using similar configuration, some of our research partners did some experiments in Italy towards the end of last year and demonstrated a free space optic communication system operating at 320 gigabits per second, as well as 1.28 terabit per second transmission, which is the highest transmission speed for any wireless communication system. Because this technology uses most of the devices which are also used in optical fiber networks, it's easily compatible with the existing optical fiber infrastructure. And as we don't have any optical to electrical conversion, we have a protocol and data rate transparent communication system. So what does this mean? Basically means the necessity of reconfiguring a transceiver is eliminated even when the nature of the transmit signal changes, say by varying bit rates, signal formats from analog to digital, or wavelength channels. So this last point here, protocol and data rate independent nature of this system makes it a suitable candidate for implementing our proposed developed radio on free space optic system, which is shown on the figure below there. So for transmission through the atmosphere using the proposed radio on free space optic system, direct optical amplification and emission of the radio over fiber signal from ROF module is utilized. And in this configuration, it's possible to transmit multiple RF signals based on various wireless services, for example, cellular wideband CDMA signals, wireless local area network signals, WiMAX signals, etc. So just to talk a bit more on this proposed radio free space optic technology we've developed, it's basically a combination of the new generation free space optic system, which was just described, and radio over fiber technique. So radio over fiber is a technique of modulating RF subcarriers onto optical carriers for distribution over a fiber network. This technique has several advantages, which include transmission and distribution of RF signals at low cost, longer distance, and low attenuation. And it's usually used as a solution for broadband wireless connectivity in the backhaul, interconnectivity of distributed antenna systems to improve indoor coverage, as well as interconnectivity of distributed cell site architectures. Unfortunately, it has a disadvantage that ROF technique is dependent on the availability of installed optical fiber infrastructure. So in the absence, we can economically and conveniently use free space optic communication links as a replacement of fiber, and in that situation, we have what we've proposed, the radio on free space optic communication system. Some of the application areas are outlined there, and like an application scenario is shown on the figure on the right. This slide shows the photograph of the RFSO terminal antenna we developed on the top left. On the top right is the RFSO antenna, internal optical path, and devices layout. The table below shows a summary of the specifications of this RFSO system we've developed. Just to highlight some key parameters, the operating wavelength of the system is 1.5 micron wavelength. The transmit power in our experiment, we just set it to 100 milliwatts with just about 20 dBs, but in fact we can operate this antenna up to 500 milliwatts. The antenna aperture is 8 centimeters, the coupling losses have been minimized to just about 5 dBs, and the beam divergence is made narrow so as to transmit as much optical power to the opposite receiver. So the antenna is optimized for transmission of RF signals with frequency range of operation of more than 5 GHz, and is designed in a way to suppress most of the atmospheric turbulence-induced effects like scintillation, beam wonder, and infrared fluctuations, which usually have a significant impact on the performance of RFSO systems in the atmosphere. This slide shows the experimental setup for the evaluation of the RFSO system we have developed. We have at one side, should be on my right. Okay, on the right-hand side, at one side we place signal generators to produce the various wireless service signals we are going to test. At the next site, we have signal analyzers and other devices for measuring the quality of the transmitted RF wireless service signals. At both sites, we have two interface units, an optical interface unit shown as optical IF unit, and an RF interface unit shown as RF unit. The optical interface unit consists of a wavelength, multiplex, and the multiplexing device, post and boost amplifiers, as well as optical circulator to separate or isolate the transmit signal, to separate and isolate the transmit and receive signals. The RF interface unit basically consists of the ROF modules for optical electrical conversion of the corresponding wireless service signals. So the signal generators produce separately the RF-based signals at -20 dBm. They are fed into the RF interface unit consisting of the ROF modules with optical modulation index of about 10%. The optical signal from the RF interface unit is fed to the optical interface unit, where it is multiplexed and amplified by a 100 milliwatt fiber amplifier. It's sent to the rooftop using fiber cables, and the free space optic antennas on the rooftop transmit the signals over a 1 kilometer path with corresponding transceivers, where the reverse process is done, and the signal generators measure the quality of the transmitted RF signal. The slide just shows some photographs of the actual devices we used in the experiment. The left is a photograph of the antennas set up on the rooftop of one of the university buildings in Waseda. So you will note that we also have a weather measuring device to record the changes in the weather condition and correlate it with the performance of our system. The photograph on the right shows the devices layout on the in the laboratory, and it's mostly the devices I've just described in the previous slide, which we're using to measure the quality and record the data for performance evaluation of the system. This table here shows the wireless signal wavelength assignment for the downlink and uplink, as well as the operating frequency for the different wireless service signals we are investigating. It's found in the paper in the proceedings, so you can refer to it if you cannot read these values. And the figure below is the optical received WDM spectrum, showing the 4 channels carrying the different wireless service signals. From left is the terrestrial television broadcasting carrying signal wavelength. The next is the cellular wideband CDMA signal carrying wavelength, and the last two are IEEE 801G, 802.1G, and 802.1A respectively. As a first example of the performance evaluation of this RO-FSO system when transmitting multiple RF signals, I'll show here is when transmitting a mobile cellular wideband CDMA service signal. The figure on the left shows the received wideband CDMA signal, adjacent channel linkage ratio spectrum, and the ACLR, which is ACLR. And ACLR is a figure of merit which has been specified by the 3GPP for evaluating wideband CDMA signal transmission. And the 3GPP specifies an ACLR value of 45 dB at the 5 MHz offset and at least 50 dB at the 10 MHz offset. The figure on the right shows the variation of the ACLR received optical power characteristics measured over an extended period of 24 hours. The left vertical axis in this figure is the ACLR measured in dB. The right vertical axis is the optical power measured in dBm, and the horizontal axis is time. The blue dots is the ACLR at 10 MHz offset, the green is the ACLR at the mark -5 MHz offset, and the red dots represent the mean received optical power. You can see from the figure that there is a correlation with the variation of the received optical power to the variation of this ACLR. And fortunately, that the ACLR values measured at the -5 MHz offset consistently show good performance because they are above 45 dB as specified by the 3GPP. But unfortunately, for the case of the ACLR values measured at -10 MHz offset, they fall below the -50 dB value which has been specified by the 3GPP. The reason for this shortfall is the limitation of the 2 GHz ROF module we developed for the wideband CDMA signal transmission, and unfortunately there was some background noise which was generated from the boost amplifier